welcome guys to this new edition for the seminar for ModMath, research seminar in ModMath. And this time we have the speaker for this session is our very good friend, Christian Meyer. Thank you, Christian, for accepting to give a talk in the seminar. And as I always say, Christian is actually a friend of this house, right? He's almost a founder guest of ModMath. So it's always a pleasure to see you, Christian. And well, today he's going to talk about, I guess I understand it's a very new topic, right? So nice to have this new topic in our space. And Christian, welcome. Thank you again. And the ModMath audience is yours.
Yeah, thank you, Sergio, for the very warm welcome and for the invitation, giving me for giving me the opportunity to talk here today. It's as you said, it's really a brand new topic. The preprint, we are still working on the very last epsilons of the preprints for that. So it will be, I hope that we will put it on archive in the next weeks. It's and the topic is convex relaxation of parabolic optimal control problems with combinatorial switching constraints. And I should mention that this is joint work with Christoph Buchheim and Alexandra Grütering, both also from Dortmund. And yeah, maybe that's typical for Corona times that you start working together with the local heroes because you are not able to travel. Okay, that's that's the story maybe behind. I prepared some proofs for the talk, but I don't know. I'm not sure whether I have enough time to present them. So we shall see. If I'm running out of time, I will skip them. Otherwise, I will show you some details of the proof. This is what I just wanted to say in advance. Okay, so let's go into the subject. And first, here's the outline of the talk. So I will start with the optimal control problem we are considering. And most of the contributions of the how to say ingredients of this optimal control problem are standard, and but the particular feature of the problem under consideration is, as the title indicates, combinatorial or combinatorial switching constraints. So we are searching for particular controls only attaining values 0 and 1, and which model switches of a certain PDE system, so to say. And this gives rise to some discrete binary discrete structure in the background. So this is no longer a convex problem. And of course, in discrete optimization, convexification, convex relaxation is an important issue. And therefore, we ask for the convex hull of these switching constraints. And it turns out to be an interesting question to really characterize the convex hull of these switching constraints. And we are doing this by means of, kind of projection and then cutting planes associated with these projections. And this allows for an outer approximation or outer description of the convex hull. And this gives rise to an outer approximation, which I will address here in the, so to say, center section of this talk. And the following two parts of the talk, following these algorithms, are dedicated to special parts of the algorithm where I explain how to solve these or to perform these steps of each iteration. And at the end, I will end up with some preliminary numerical results illustrating how this algorithmic approach works in practice. So let's start with our optimal control problem. That's how it looks like, and it's pretty much standard, except for this constraints I will explain in a minute. What is it? Yeah, we have the control U, and it's just time dependent, and it enters the this parabolic PDE for the state Y. Here in terms of the right-hand side with given form functions psi. So these psi j are given form functions, and their minimum regularity is h-1, but you can also think of L2 functions in space, yeah. And these are weighted with these uj, and the uj are our control variables, and we have this standard tracking type objective with some desired state yd, and we have here some Tikhonov regularization term with the Tikhonov parameter alpha. Why we have here 1/2, I will explain in a minute. So, and the particular, so this is more or less everything is standard, and the particular, so the special feature of this problem is the switching constraints covered here in this set D, or by this set D. What is this set D? It's a subset. So we have various instances for it, and it's always a subset of the space of bounded variation. And the functions should only or shall only take the value 0 or 1 almost everywhere in time. So 1 is switched off, and 0 is switched on, and 0 is of course for switched off. So we can switch off and on these form functions to heat up a body. This is what you can keep in mind. And then you also see why we have 1/2 here. It's like you do not want to prefer whether it's switched on or off. That's not, of course, we could also say, okay, we take a 0 here, then you would prefer if some heat source is switched off, but we don't want to do that. And the interesting thing about this 1/2, and I guess for people from discrete optimization, this is classical for me, coming from continuous optimization. This was a nice observation that no matter what control you choose, if it's coming from this feasible set, then of course, because it just can take the value 0 or 1 here, this L2 norm is always the same. And so more or less, if you are in this feasible set, the Tikhonov term here always attains the same value. And so it doesn't matter what you choose for alpha. And coming from optimal control, this is interesting, because usually alpha is a quite delicate issue, the choice of alpha. If you come from inverse problems, then okay, you know, alpha have to be chosen, well suited to the error in the measurement of the data, and you have, for instance, the discrepancy principle to steer the value of alpha, and so on and so on. And here it doesn't matter. So just choose alpha what you want. That was for me at least a strange observation, but it's not playing an essential role for the rest of the talk. Of course, everything here is linear and strictly convex, but of course the set D, because of these binary constraints here, destroys convexity, of course. So, and what I also would like to mention is that everything here is just so for the rest of the talk we will concentrate on the set D and how to deal with that. And I'm pretty sure that you can transfer everything we've done here to many other PDE problems. So you can also consider hyperbolic PDE here or other objectives, but it should always be the rest, except for the set D, everything should be convex. That's important. Okay. What are examples for this set D of switching constraints? You could think of what we call pointwise combinatorial constraints. So you have a function in BV, and the TV semi-norm here should be less or equal some given constant sigma, which means in our context, when u just is allowed to take the value 0 or 1, so it's a switching function, then this constraint just means to bound the TV semi-norm just means, okay, you just allow for sigma switches, sigma number, I don't know, 5, whatever. So you're just allowed to switch the control on and off for 5 times. And but we can also include other pointwise constraints here. So not just only 0 or 1, but a proper subset here of 0, 1, which for instance could model your own at every time point only one switch of this j, of this n switches uj can be switched on. This, for instance, could be covered by this set u, just for an example. But we could also consider switching point constraints. What is that? Again, we have a BV function which is only allowed to attain the value 0 or 1, so a switch. And we denote the essential jump set of u by ju. This is the point of discontinuous. This is the time points where u is discontinuous. And if you have a BV function, you know, okay, this is countable, but of course, here we just we would like to have that there are only sigma as before discontinuity. So we are only allowed to switch sigma times, and these time and we can account for constraints on the time points, which could, for instance, model minimum dwell constraints, which means, okay, there should be a minimum or there should be a minimum time distance between 2 switches, because for technical limitations, you cannot switch arbitrarily fast. So this can be modeled by this type of constraints here. So this, if you wonder what does or what do switching constraints mean, here you have 2 examples. This fit into our theoretical framework, so to say. So, and the first question is, of course, is the problem well posed? Do we have a solution? And for that reason, we need 2 assumptions. First of all, we need a bounded set in BV in the space of bounded variation, functions of bounded variation. And this is both, in both cases, is satisfied. Here we just see, okay, we have here the limitation or the bound for the total variation, and here it's also this is also more or less a bound for the total variation. So both sets fulfill this, and we need a second assumption that D is closed in some Lebesgue space LP for some fixed P less than infinity, and you can verify also this for both instances I mentioned. So, and if these, and of course, the set D should be non-empty. And if this set D fulfills these 2 assumptions, then you can prove that there is a global minimizer for our optimal control problem. And it's not hard to see. It's a standard direct method of calculus of variations. And of course, always when we do this direct method, we start with an infinite sequence, a minimizing sequence, and we need some compactness here. And this comes out of BV. So if you have a bounded sequence in BV, but by assumption B1, we have a bounded sequence in BV, then you know there is a subsequence which converged strongly in LP, and for every P less than infinity, and then you see already, okay, assumption D2 comes into play, and so on and so on. So it's not hard to prove that. Okay, and you can prove this existence result for much more general problems. So you do not need a linear PDE for that. Could also allow for a semi-linear parabolic equation. That would be no problem. Okay, So that was not the interesting case point. What is interesting is, of course, how to solve this problem numerically. And there is a whole zoo of different methods. And the first one is maybe this, what is classical called first discretize, then optimize. So you take the whole problem, discretize it by means the PD, for instance, by finite elements or whatever you want. And then you end up with a huge mixed integer nonlinear program. So it's nonlinear because of quadratic objective, and you have the PD, and it's, of course, you have this integer constraints because of this switching. The controls are just allowed to take binary values, and then you, because of discretization, it's usually typically it's a huge system, depending how you resolve your time interval and your domain, and then you apply your favorite MANLP solver. So there's just a bunch of methods for this, and I guess some of you are much more familiar with that topic than I am, so I will just skip that. Okay, this is not what we want to do. We want to work in function space, and there are function space based methods, and one is this combinatorial integral approximation with this nasty abbreviation CIA. Okay, whatever. What the people do there, it goes back to Saga, Christian Kirches, Paul Manns worked on that a lot. It's so you convexify the problem, and then you solve the convexified problem, and then you apply a rounding strategy because if you convexify the whole problem and solve that, this solution won't be discrete or binary valued anymore. So what you do is you apply a sophisticated rounding strategies that accounts also for the switching structure and so on. So this is what is known as combinatorial integral approximation. It's like solve convexified problem and then apply rounding afterwards. Of course, tailored rounding, like sum up rounding, but sum up rounding often does not account for switching, and then they modified their rounding strategies and so on. Okay, what you can also do, once you know that you have a discrete valued control and you have a bound for the total variation, then you know, okay, it's just a switch, it's a switching function with the finite number of switchings. And then you know what we just need to know is the time points where you do have where you switch it on or off. So what you can do is just turn everything into a problem on these switching times. Yeah? So you throw out your whole control and just you optimize for the switching times. This can be done, and there are people working on that. And a disadvantage in this context is, at first glance, it seems, yeah, that's the way to do, because you do not have you do not have any longer a problem in function space. You're just searching for a fixed finite number of switching times, and then you have if you at the end it's an NLP set. It's an NLP in finite dimensions. But if you do so, even if everything else, PDE and your objective and so on is convex, strictly convex, so the whole problem is strictly convex. If you turn it into this problem concerning the switching times, it becomes non-convex, so highly non-convex, and then so you lose this convexity, and then it's hard to find global minimizers and so on. But anyway, you can do so, and people work on that a lot, so it works. Another approach is penalization with non-smooth penalty functions. L0 norm, which is not a norm, of course. L1 norm, multi-bang is also something if you have not just binary. It can be done if your your switching function is should be allowed to attain many values and so on. And there are also many people working on that. It's I don't know, Christian Claesson, Kunisch, Fumito, Daniel Wachsmuth did something for some hard thresholding algorithms and so on. So, and I mentioned few names here, and I pretty for sure I forgot many people working on that, and I'm sorry for that. So there's many things you can do, and if we have a closer look here to this combinatorial approximation, then you first solve a convexified problem. And if you're coming from discrete optimization, of course, convex relaxation is always important. Just think of branch and bound. Yeah? So, and the issues now, or the question we asked ourselves last year was, what is a proper convexification of the problem under consideration? And of course, now I come to this convex hull of the set D. Convexified problem, I mean, here everything is convex. The objective is convex, the PDE is convex, so we just have to convexify the set D. And how the question is in which space? Okay, the space for the controls, maybe it's LP. LP, P was the number or the integrability exponent from our assumptions. For the rest of the talk, just think about P being equal to 2. This is a Hilbert space, and everything is nice. But it could also be some other P. Okay, and of course, convexification. We take the convex hull of D, and then not every in function space, not every convex hull is closed. So we just take the closure in this space LP, and this would be at first glance a proper convexification. So, and the question is now, what is this set? And this is it turns out to be kind of delicate issue. What is a convex hull? And this was the central question for this paper, for this project. And first, the counter example. Well, if for instance D is this set, which is probably the most easiest set in this context you might imagine. So here we have only one switch. It's only allowed to take the values 0 or 1, and the total variation should be less or equal 1. So you just switch it 1, and then you are done. From 0 to 1 at some time point, or 1 to 0 at some time point, and that's it. This is the set D. And well, if you think about if you would ask me what's the convex hull of that set, I would say, okay, I just turn here to the interval, to the closed interval, not just 0, 1, but from the interval from 0 to 1. So this here. And it turns out this is not the convex hull. Because, and here's the counter example. If you take this function here, which is 0 at the beginning, then you jump to 1/2, and then you jump back to 0, and it's clear you're fulfilling this. The total variation of this function is 1. You jump to 1/2, and then you jump back to 0. So the sum is 1/2 plus 1/2 is just 1. But it turns out that you are not in the convex hull for every P, even for P equal to 1. So, and the point is that this, if you think about it, it's not so easy to understand why it's not in the convex hull. The reason behind is maybe that this convex hull, because of this switching structure, you are just allowed to switch once. You have some hidden monotony. If you start with 0, you can just go up to 1, and that's it. If you start with 1, you can just go down to 0, and that's it. And here you go up to 1/2 and down again to 0, and this cannot be constructed by functions in the set D or convex combinations of this. So you do not end up in the convex hull here. That's maybe the reason or the explanation what is behind that. So, in other words, if we consider such a set D and consider the convex hull, it's not what you expect at the first glance. And we were really, for this very, very easy example, just one D, just one switch, we try to characterize tight the convex hull, but it was hard, and we were not able to give very close and brief characterization of the convex hull. And then we thought, well, why do we need the convex hull? What do we need when we apply a kind of an algorithm for that? Then at the end, the convex hull or tight and close and brief description of a convex hull is not that interesting. What we need are cutting planes to cut off non-feasible points. So we need and this was a starting idea for an, let's say, indirect characterization of the convex hull. So this is then this algorithmic framework I try to describe. As I said, we want to design an outer approximation algorithm, and for that reason we need an outer description of the convex hull by means of supporting hyperplanes, yeah, and which gives us cutting planes to cut off infeasible points. And if we go to finite dimensions, then such separation algorithms, so the characterization of cutting planes, if you have a non-feasible point and so on, this is known for many polytopes and other convex sets. And the idea was, okay, here we are in function space and everything is not so clear. So try to project this set to a finite dimensional set, Rm, and then hopefully we can use then separation techniques for convex sets or polytopes. Maybe this is even a polytope in finite dimension. Well, and how can we project such a set to finite dimensions? Well, what we did is projection via local averaging. How does that work? Well, we take for this purpose, we take our time interval and cut it into capital N intervals, such that we get a pairwise disjoint partition of our whole interval. So the subintervals should not overlap, and we need that they cover the whole time horizon. Okay, and on each such intervals, we consider just the mean value of the function u, of an arbitrary control u here. And so lambda of I is just here the Lebesgue measure, so the length of the subinterval, more or less. Okay, and we do that for every component of our control vector, and for every such subinterval, we collect all these mean values and write them into this vector here, and this gives rise to our local averaging operator. And it's well defined. You do not need a BV function here. It's of course here you just need this integral to be well defined, so it's well defined on L1. Okay, and what will also be important is this set CD, which is the convex hull. So we take an arbitrary control in D in our feasible set, and we take the projection of this. So we end up in a vector in Rm, and then we take the convex hull of all these vectors. This will be an important set in the sequel. So, and what you can prove is the following: what if you take a sequence of partitions, and which shall fulfill, first of all, the partition should become finer and finer. So the mesh size, the length of the subintervals should go to 0, and all these intervals should be nested. So you just think of, you start with an initial partition and then you halve every subinterval to get the new one. This is maybe the most easiest construction you could imagine in this context. And if you take these partitions and consider always these local averaging operators, then you have this description of the convex hull, of the closure of the convex hull in LP. So we take the intersection of all LP functions such that if you take the local averaging of these functions, you are in this set CD, which was this set, convex hull of all functions in D, if you apply the local projection. So, and yeah, I already speak nearly half an hour, so maybe I skip the proof. So this is the proof. It's not so complicated. Maybe I just mention some details. So we want to show that two sets are equal, and this that to show that the convex hull is contained in this intersection, it's straightforward. This is really one line, but so the other inclusion, this one is important one. So we start with some function in the intersection, and by the definition of the intersection, we find that it's, because it's in the convex hull. Here, if we look at this, there's the local projection is in the convex hull of these local projection from functions in D, and this is what we use here. So the local projection of this function U is a convex combination of local local averaging operators applied to functions V here, and these functions are D. And what you do then is you throw out the local projections here and just consider the function UK, so without the local projection. And what you can show is by construction, this satisfies these functions UK satisfies this equality here. And if we have a closer look at UK, we see, okay, because it's in the convex hull of functions in D, so its essential supremum is bounded. So we can select a subsequence converging weakly star in L infinity, and this allows to pass to the limit. This weak convergence allows to pass to the limit in this equation. And so we get this. And this holds for every interval, for every partition, no matter how fine the partition is. And so and this is the link then to show at the end the result, because, okay, if this holds for every partition, we take an open subset U of our time interval, and we consider all these intervals which are contained in U, and we collect them in the set AK. And what you see is for K going to infinity, finer and finer partition, this is an exhaustion of U. And on the other hand, it's a reunion of intervals. And because it's a union of intervals, and on every interval we have this equation, so we have this equation also on the set AK. And because it's an exhaustion of U by means, and then this equation carries over to the open set U. And now, you know, for every open set, this holds, and then the regularity of the Lebesgue measure implies that this holds for every Lebesgue measurable set. And this gives that U is just equal to U tilde. And because UK was in this convex hull, and U tilde is just the weak limit, then you obtain that U tilde is in the closure, the weak closure of the convex hull. But because it's a convex set, the weak closure coincides with the usual strong closure, and then this gives that U is indeed in the strong closure. So let us collect what we have so far. We have a convexified problem here, and I reduce the whole problem to the control only. So I throw out the the state, which is just the solution of the parabolic equation, and I denote the solution operator by capital S. This is standard in optimal control. So throw out the PDE, and here we have our convexified problem. And what we have seen now is that we have this description of the convex hull. Yeah, and the question is, what is that good for? What should we do with that? Well, and now this set CD comes into play, because we know this is a convex enclosed set in Rm, so it can be described as the intersection of all supporting hyperplanes, or intersection of all hyperplanes here characterized by A, B. A is the normal vector to the hyperplane, that are induce valid inequalities for this closed and convex set. Standard description of convex sets in Rm. And of course we can weight the normal vectors so that the whole I don't think we need it for B. I'm sorry for that. This should just be the A. This should just be the A here. That the normal vector is as maximum entry 1 by weighting the inequalities here. This is what we assume for the rest of the talk. So, and if we keep this characterization of this finite dimensional set in mind, then we end up with this algorithm. So what do? In each iteration, we solve a problem of this type here, where here you see these hyperplanes, these separating these supporting hyperplanes or valid inequalities for the set CD. So you solve this. If you are in the closure and convex in the convex hull of D, then we are done. We have solved our convexified problem. Otherwise, we know by this characterization here, if we are not in the convex hull, then we know that we are not in this intersection here. So there has to be some projection, some local averaging, that we are not in the set CD. So we were searching for such a projection. So determine intervals. Maybe we have to refine for this, such that UK is not in the set CD. This is possible because of our characterization. So, and once we have found such a local averaging operator by refining the interval, we take for this fixed UK and its projection respectively, we take the most violated valid inequality for the set CD. So this is the HD were the set of all valid inequalities for CD, and we take the most violated one. And this gives our new cutting plane. This gives the new cutting plane. This cuts off UK. So UK won't arise here anymore, because we take this new cutting plane, this mostly violated cutting plane, and add it to this set of inequalities here. And in this way, one cutting plane after the other is added here. So you cut off one infeasible point after the other. So, and indeed this works. So what we can show is, if you take a sequence of partitions of our interval 0t with vanishing mesh size, so we make it finer and finer. As before, all intervals are nested. This is what we had before. And we need an additional assumption, which is quasi uniformity. What does this mean? You need that the relation between the largest and the smallest interval in each partition should be bounded by some constant kappa. So you are not allowed to be very fine at some point with the intervals and very coarse at other parts of the time horizon. And we need that the Tikhonov parameter alpha is strictly positive. And then we can show that the sequence of iterates generated by this algorithm indeed converge strongly to the unique global minimizer of our convexified problem. So, just one word, the convexified problem is uniquely solvable. Why? Yeah, because it's convex, and because of alpha, the Tikhonov parameter, strictly greater 0, it's strictly convex. So there's just one global minimizer, and our sequence here converges to that. And maybe I skip this proof and just go back to the algorithm, because, well, so far the algorithm has still some two delicate open issues. And the first one is how to solve these problems here. I mean, these are still optimal control problems. Huh? Think about that. Here's the PDE is hidden here. We have control constraints, box constraints on the control, and here's some finitely many inequality constraints. Okay, so we have to solve these problems, and we have to find the most violated cutting planes. And for that, we need a good outer description of the set CD. So we need a tight and handy description of this set HD, which collects all cutting planes or all valid inequalities for this set CD. And this is what I wrote down here. This is what is left to do. Solve these optimal control problems arising in each step, and solve these finite dimensional separation problems. So find the most violated cutting planes. And I will first focus on this separation problem. And yeah, I'm a little bit frightened because of that, because as you know, I'm no expert for discrete optimization. So I just wrote down what Christoph Buchheim told me. So now we are in these projected sets, and we would like to find, it's about the characterization of these of the finite dimensional convex of these finite dimensional sets arising from projecting the functions in D. And now, in this can't be answered in general, so you really have to look at each particular instance for the set D individually. And let me start with these, point-wise combinatorial constraints. So we have, what was it? We have a function in BV, and at every time point, almost everywhere in time, we are in some subset of binary vectors, and the total variation should be less or equal sigma. And what can be proven is that for every local averaging project operators, pi, so given arbitrary partition, apply this local averaging, the arising set here is a 0-1 polytope. So that's the good news. It's a polytope. So we know that we can characterize it by finitely many hyperplanes. Yeah. Let me just skip that proof. And well, although we know it's a 0-1 polytope, experts in discrete optimization, they know, yeah, nevertheless, the separation problem might become very ugly. It's in general, it's NP hard, but at least there are cases where it can efficiently be solved. And one case we also considered for our numerical experiments is this set. So just one switch, the set U is just 0-1, so on and off. the total variation is limited by sigma, and we start with 0. And then you have this characterization of the set CD. You see, it's here are more or less these valid inequalities, and it's as far as I understood, I didn't understood a lot concerning this theorem, but as far as I understood, it's a minimum set of valid inequalities. So every of these inequalities is really necessary to characterize the set, and they have a kind of easy structure. So it's really possible to efficiently solve the separation problem for this kind of set, and also to find for a given vector the most violated inequality. So this can be done. And what about the other instance we had? We had these switching point constraints. Here I recalled them again. And what can be proven is, again, for every local averaging operator, the set CD is a polytope, which is good news. And moreover, if we look at this special case of minimum dwell time I mentioned at the beginning, where the time between two switchings is limited from below by some minimum time distance s, then we can show that there is a separation algorithm which is with polynomial runtime. But nobody knows, at least we don't know, how this algorithm looks like. So it's a typical discrete optimization argument. You can prove that you can optimize in polynomial time, so you know that you can also separate in polynomial time, but I'm out. So please don't ask me anything concerning that. So let's turn to the other issue of our algorithm. So we know now that at least in some special instances, we are in the position to solve these separation problems, to find the mostly violated inequality efficiently. But in every iteration, we also have to solve an optimal control problem. And these optimal control problem look as follows. So here we again have our objective with the control to state map. We have these box constraints on the control, and we have these finitely many inequality constraints coming out of our local averaging projections, so to say. Okay, and I just want to recall the state equation. What is S? S was the solution operator of this parabolic PDE, yeah? And where the control enters with this given form function psi I. And for the right-hand side here, I need some notation. I introduce this capital psi, so to say, of U here as abbreviation for the sum here appearing on the right-hand side of the state equation. And then you can think about, well, this is a linear operator, what's its adjoint, and the adjoint is then given as this. So if you take a function in L2 in this Bochner space with values in H1, then the adjoint looks as follows. So you take here the dual pairing of the form function with your input W, here called W, and then there's a function comes out, which is a vector function in L2. And yeah, this is the adjoint of this operator psi. And this adjoint will pop up in the KKT condition for this problem. And well, if you're coming from optimal control and you look at this, it's a little bit boring. I mean, here we have a convex objective, linear control to state map, box constraint, and finally many inequality constraints. Yeah, should be possible to find in the literature some Lagrange multiplier theory for that, but to be honest, I wasn't able to find something for this. So we had to prove it, but it's not so complicated. But as we are in function space, we need some Slater type condition, and what is best suited for our settings is this later point for the control constraints. So it's fine if there is a function you had, which is really strictly greater 0, strictly less than 1 almost everywhere in time, and fulfills our cutting plane inequalities, then you can prove that you have this optimality system, and what comes out is what you expect. An adjoint equation with an adjoint state P. Here you have the derivative of the objective with respect to the state. We have this gradient condition here. Mu A, mu B are the multipliers for the box constraints. So greater equal 0, less or equal 1. Here the box constraints. And this lambda is a vector in Rk, the multiplier for the finitely many cutting planes inequalities. And in all cases, we consider this later condition is fulfilled by the constant functions 1/2, for instance. Okay, and so now we know that this is KK, these are the necessary condition because of convexity. This is also sufficient. So if we solve this, we have a problem, we have a solution of our problem. And of course, Juan Carlos worked a lot on this, how to solve this semi-smooth Newton. So we reformulate all this in terms of a non-smooth equation. Here the operator P pops up, which is a mapping of U, the control, to the solution of the adjoint equation. So first of all, you solve the state equation and you plug in the state here and you solve this backward in time equation. Okay. And then this is an equivalent formulation of the KKT system by means of these complementarity functions min and max. And what's nice is, if these form functions are a little bit more regular, you don't need functions for this. You just need elements of dual or elements in negative Sobolev spaces. You can, for instance, account for boundary measures or something like that. That would be no problem. Then this mapping F here is Newton differentiable. Okay, and then you can apply a semi-smooth Newton method for that. So it's not, of course, because of min and max, it's not differentiable, but it's Newton differentiable, and there's whole machinery for Newton methods for this type of differentiability. And one might then ask, will such a Newton method converge? Newton differentiability is not enough. You need also regularity, of course, of the Newton matrix or the associated operator, linear operator in function space. And you can't expect that here. Why? Because if you add more and more and more cutting planes, then the normal vectors will then at the end become linear dependent. And then you lose, and then the Newton matrix will become rank deficient, so irregular. And but in our numerical experiments so far, I have to admit, I don't know what to do there. However, in our numerical experiments so far, we haven't seen that. So it always a more or less moderate number of cutting planes were sufficient so far, and for that reason, the Newton system was always solvable, luckily. So this is an open issue. We have to think about that. So that was the algorithm. Let's come to the numerics. So the test case is our most simple set we had. So just one switch with the value 0, 1, starting in 0. So everything switched off in the beginning, and the total variation, so the number of switchings, is limited by sigma. We discretize the PDE by standard linear finite elements in space, implicit Euler, time stepping in, in time, and this is implemented in U, so C++ library for PDEs for finite elements. in this case, we had this rather simple description of the set CD on these valid inequalities arising through these local projections. And because this description was rather handy, the separation algorithm to find the most valid, most violated valid inequality is it can be performed very fast, and for that reason we can use the time mesh coming out of the discretization of the PDE for this local averaging. So from a practical point of view, I would say it doesn't make sense to take a finer grid for the local projection than what you have for the PDE anyway. And because the separation algorithm is so fast here, we can use this. So then we have to solve Newton's semi-smooth Newton or perform a semi-smooth Newton iteration in each step of the outer approximation algorithm. How is this done? We do it in reduced form, so everything is reduced to the control only. For that reason, we have to solve in every new step state and adjoint equation, which is done by Dune's inbuilt CG method with algebraic multigrid preconditioner. And then the arising Newton system reduced to the control only is solved by MinRes, which for what reason ever, I don't know, performed better than CG. But we also just applied a very cheap and maybe the most easiest preconditioning via equilibration. So, and yeah, here's the test case. So we took the unit square, capital, the time horizon is 2. We have just one form function given by this function here. This is the desired state. And and of course we want to, now the interesting question is, how good does our algorithm perform? And the question is how to measure that. And we wanted to at the end, you want to solve a convexified problem, a convex relaxation. And so maybe a good test or a good way to evaluate the performance of the algorithm is to compare with the naive, what we call naive relaxation, where we just replace these binary constraints by the interval, which we have seen is not the convex hull. It's a larger set than the convex hull. So we expect that if we optimize with respect to this set, we get a because it's larger than the convex hull, we get a smaller objective because the feasible set is larger. And at the end, we compared what we want to solve at the end, of course, is the discrete problem with this set, no convexification at all. And what we do is we plug it in after discretization in Gurobi and solve with the Gurobi inbuilt MENLP solver. Okay, and this is what comes out. Big table. So here we have the result of the NLP solver. Here's the result of this naive relaxation, and here's the result of our, say, tailored convexification. Of course, the number, this is here the discretization, the mesh points in each spatial direction, and this is the number of time intervals. Of course, the number of the discretization is limited because of Gurobi. I mean, if you discretize everything and plug it into Gurobi, you can't do it on arbitrary fine meshes. And yeah, what comes out is maybe this is the most important column here. This, of course, the objective for the discrete feasible set is much larger than the objective for the relaxations, because by convex relaxations, of course, the feasible set gets larger and the objective is decreasing. But we see that the objective for the naive relaxation is much significantly larger than in case of our convexification. And as I said, the naive convexification, convex relaxation, is not the convex hull. It's larger than the convex hull. And you see that we filled the gap to what we want to have at the end. This is a real discrete problem. And we filled the gap between the objective in case of convexification to the non-convex problem by these numbers here. Yeah? So this is comparison of our objective, the objective of the naive relaxation, which is less, to the true objective of our of the binary problem, so to say. And you see we have a significant reduction of this gap. So indeed, our convexification performs better than the naive one. And then at the end of my talk, we have seen that the closure of the convex hull of switching constraints with TV bounds is not what you expect. So it's not like replacing 0, 1 by the interval 0, 1. But it can be approximated by means of this local averaging procedure I presented. And this local averaging can also then be used for an outer approximation algorithm. And provided you have these, you can solve these finite dimensional separation problems, which means to find the most violated inequality. And the solution of the arising cutting plane problems then can be done by semi-smooth. And I would like to mention that it's not that we get better results compared to the naive relaxation. Also, the naive relaxation is not straightforward to solve because you have here this PV, this bounds on the total variation. And how to solve this? How to efficiently solve an optimal control problem where you have bounds on the total variation. So this is not a Hilbert space. So squaring the norm, the semi-norm doesn't help a lot. You have to characterize the subdifferential maybe of BV, yeah, and it's really becoming disgusting. Okay. So we have better bounds, and we have what I would say a rather, say efficient algorithm. What remains to do is, okay, so far we just can solve convexified problem. At the end, we want to solve not these convexified problems, but the original ones. So we have to embed everything into a branch and bound algorithm, or maybe apply some sophisticated sum-up rounding or rounding strategies in advance to attack the original problem with the binary constraints. And what is in particular interesting for me is switches which are distributed in time and space. And of course, if you have higher dimensions, then BV is getting, space of bounded variation is getting really interesting. And yeah, this is something I would like to address in the near future. So that's all. Thank you very much for your attention.
Thank you, Christian, for this very interesting talk. I would say that it's very technical, but very, very interesting. So we have time for questions. This is the time. Questions, comments, please. Lucho, please go.
Thank you. Hi, Christian.
Hi.
First, thank you for the very interesting talk. I have two very naive questions because it was plenty of information today. And can you please put again the results slide? Because there was something I could not get. Yeah. This first part, this min LP, this refers to a natural solution, also to a feasible integer solution for the problem?
Yes. So
Okay.
what we did is discretize everything and then just plug it into Gurobi.
Okay.
So in Gurobi, this is our problem solved.
Okay.
So don't ask me what Gurobi does.
Okay, and Gurobi returns this as a feasible solution. And then you compare this with two bounds, one coming from the naive relaxation and one coming from this tailored relaxation. Yeah. Okay, and you prove that this relaxation is indeed better than the naive one. Yes. But how is this field gap again computed?
Yeah, it's just it's just you take the objective values here we obtain with our relaxation, and you have a gap of you see the gap to what is a true objective coming out of Gurobi. Okay. And you do the same with the objective coming out of the naive relaxation. Okay. And you see the gap is larger here. And this just field gap just gives you the reduction. How much? What is the reduction of this gap? Okay. 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 And thanks. What we can't answer so far is that it's getting less if the number of or if the partition of the time horizon is getting finer. This is something we observed, and I can't explain. So it looks like if the partition is fine enough, probably the difference between the two relaxations doesn't matter so much. Or? That's true. Hopefully not. I don't know. Yeah. But on the other hand, what one really has to say is, yeah, it might happen that this really goes to zero, but I mean, it's not that the naive relaxation is easy to solve because we still have these PV constraints in here, and I don't know how to implement this efficiently. Yeah. In contrast to this, our problems which arise in each iteration of the outer approximation problem are more or less easy to solve. It's like bound constraints, box constraints in optimal control with finite number of inequality constraints. And where the semi-smooth Newton iterations really performed, at least what we saw so far, very well. Because you just need few numbers of Newton iterations, and you apply the separation algorithm, which is in this easy test case, very easy to perform, and then you go on. It's really quite efficient. And of course, this depends on the problem structure. Okay. And last question: if you when you plug this, so you plan to plug this in a branch and bound method, then you expect it to be faster than solving the min-LP, like with Gurobi, for example? Well, I think that at least we are able to do so. Okay. Because you see, I mean, Gurobi this is the problem with first discretize then optimize. It breaks down if you I mean, this is a more or less ridiculous number of this is the ridiculous mesh size. Okay. 20 in each, and look at the wall clock time. Yeah. So that you are no longer able to solve this by min-LP. Of course, Sven Leifer puts it on huge machines in Argon, and yeah, that works. But at the end, if you go to realistic, and I mean, think of 3D PDEs or something like that, okay. 3D in space, that's no longer possible. So in contrast to this, I think we have some hope that our method still can be performed. Okay. But there's, if you go to branch and bound, it's really, there's a lot to do. So you have to really to look at the particular structure of the problem, and it's sometimes I have some hope that that you can solve a lot of computational time by taking advantage of the structure once you fixed some switching, in some parts of the domain, in other parts it automatically fixed too, and so on. So, but this is ongoing work. So we haven't thought a lot in this direction so far.
Well, thank you. It will be very nice if it works, because it will be a completely new approach to this kind of problems.
Yeah, hopefully it's competitive. I don't know.
Okay, thank you, Joe. More questions, comments?
It's not a question, it's more curiosity. At the very beginning of your talk, you explain us this variable, this number sigma. That means like the number of times you are allowed to switch, right? My curiosity is like, can you optimize this variable, or that doing that makes sense or not?
So that I understand. So that you say, okay, I want to switch. I want to avoid that I have to switch often, and to minimize the number of switching. Mm-hmm. Can this be an optimization variable?
Maybe with a bi-level optimization approach, but I don't know if doing that has any sense, or it's just like very difficult and it doesn't like apport very much to the problem.
It's an interesting question. I'm not sure. I mean, it's just a scalar variable, so if maybe one could add it as a scalar to the objective, but I cannot overview then everything. I would expect that everything is then really horribly non-convex, and I don't know the impact on the convex hull for that. Oh, it's an interesting question. I have to think about it. I doubt that I can give an intelligent answer to that. But yeah, I mean, from an application point of view, it would make sense.
Okay. Yeah, because I see in your, I don't remember in one of your complex hull, you have this sigma. I don't remember where, but you have the sigma involved in one of your sets. I think it's one of the last. I don't remember. But maybe it has.
It's everywhere. It's also here.
Yeah. It's there.
And there, it's always a bound on the TV seminar. That's interesting. I don't know. I don't know what happens with the convex hull if sigma is an optimization variable itself. I don't know. Interesting.
Okay, thank you. That was my curiosity. Thank you.
That's a good point. Thanks.
Thank you, Paula. So, more questions or comments? Christian, just one more question, like equally as a curiosity. What about the side functions? Because for the convergence result for the SSM, you established that this should be in this space HOS, but I don't know these functions exactly, where are they coming from? So because this condition looks like a little bit restrictive, I would say. So
no, it's not. It's not. You know, here's a star. It's a dual.
Yes, I know. Yeah.
So it's not HS. It's a dual. So it even need not to be a proper function.
Oh, okay.
So it's I think S less or 2 is wrong here. It should be 1. So we cannot allow for, we can't allow for H-1, so dual of H1 0. That we cannot allow for that. But we can allow, but you need to be an epsilon better.
Okay.
So this should be a 1 here. I'm sorry. This should be a 1. And it's a dual. It's a dual of a Sobolev space. So it could be. So L2 is probably perfect. L2 omega is perfect.
Okay.
But it could also be h minus 1/2 which would mean, as I said, that these form functions are just boundary measures on some, say, on some smooth manifold within your domain or whatever you imagine.
That makes sense. Thank you. With this, because I don't know, anytime I see the Z,
It's a small
tend to
star
be
here.
right.
It's a dual. It's a dual of H of some Sobolev space.
Okay, thank you. More questions or comments? I don't know what.
I have just one follow-up question, if I may.
Please, Juan Carlos, of course.
With respect to Paula's question as well, so I was thinking, if you combine, for instance, if you penalize with the total variation at some point, I guess you tried something like that, or is there any advantage that you can take also from the other approaches within yours? That's mainly the question. So for instance, as initialization strategy or something that you have considered so far.
You can, maybe this answers your question. You can also, if I go to this slide here, you can, instead of this problem, you can also consider a problem where it has the same structure here, but the feasible set is just binary, and you add the TV semi-norm into the objective. So instead of having a, so let me go to the next slide. Instead of having a hard constraint on the TV semi-norm, we could also just penalize it in here and apply the same algorithmic framework. This will also work. Is this what you mean? What you meant?
And then you have, okay, but then you don't have the discrepancy concerning the convex relaxation. Then both coincide, or what?
Yeah, convex relaxation is then a little bit no. Then convex relaxation is a little bit different because then you have to convexify your objective. So at the end, what our approach then does is approximating the best possible convexification of your objective, which is this biconjugate functional, the gamma regularization.
But convexification concerning, so you mean convexification concerning the control?
Yeah, the control of the admissible set, which is binary, but also of this with respect to the to this objective. At the end, what you do then, if you have this, as far as I remember, if you have this TV semi-norm in the objective, you and then you are at the end at the point what Paula says. So it has to work. We thought about this, but it's already half a year ago. What you do is you replace it by some scalar variable, the TV semi-norm in your objective, and you put it into your feasible set as an inequality. And then you are exactly in Paula's framework, where the bound is the optimization variable. You have the TV semi-norm here. You replace it by a scalar variable, and you want to minimize the scalar variable, and you have an additional inequality constraint. It's the same trick what Fredi, for instance, does if you want to optimize something like this, but with the L-infinity norm here. Then you replace this by some scalar variable, and you require pointwise constraints on the pointwise state constraints. Maybe you know this trick, really did some years ago. And then here you do the same. And then we are in the regime again where we have the TV semi-norm as a constraint with a bound that is part of the optimization variable. So we are exactly in the framework that Paula mentioned, and now I remember the discussion of last summer. It should be possible. It should fit into our framework, as far as I remember. But we haven't included this into our manuscript yet. So this has to be elaborated in detail. But I think so. In other words, to have TV semi-norm in the objective should be possible here. Did this answer your question?
Thank you. Yes.
Okay.
And
there are
Crystal,
more questions. Oh, sorry.
Sorry.
Go ahead.
No,
it's okay.
It's okay. It's okay.
Okay, so
Christoph told me that to have the TV semi-norm here in the objective, in some instances concerning the separation argument, should even be easier. But to be honest, I haven't followed his argument so far, so I won't promise anything. So we are still working on that. It seems to work.
Okay. Are there more questions or comments? I think so. Okay. It's not the case. Christian, thanks again for this very nice talk. I'm sure there are a lot of things to do. That's very, very promising, actually. So thanks a lot for sharing the result with us. Thank you all guys for connecting, and have a nice weekend. See you in a couple of weeks.
Thanks again for inviting me. I hope I can come to Ecuador this year.
Oh,
Corona allows. Or next year, some time again.
Yes.
Hopefully.
Bye.
Okay.
See you.
Bye.
Bye.
See you. Bye.
Thanks.